Alrighty, welcome back to operating systems. So your midterm is now written and ready for you. Yay! Yay, my part's done. Now you have to do your part. So today, midterm review, here to help you. So this is a choose your own adventure lecture. What would you like me to do? So your two main options are I can whirlwind review everything we've done so far, try and point out the important things, or just do a past midterm and try and guide you what to do. So anyone, what would you like me to do? Yeah?
Can you cover the final 2022 question 1 from lecture 7?
2020 from lecture 7, what is that? Do you have that off the top of your head from our lecture 7?
Yeah, slide
Slide
10.
10. Sure. So what is it? It is something like plus. So we have a program, whoops, you can't see what I'm doing. So we have a program something like int main void that goes int I equals 4 while I does not equal 0, int PID equals fork. If PID equals 0, I minus minus, else print f %d new line I exit 0, and that's pretty much it, right? All right, so we want to do this. This looks like fun. So the question says for each program, whatever, state whether it will produce the same output each time it is run, whether it may produce different outputs when it's run multiple times. Explain why this program, where the hell is my camera pointing? Explain why it happens this way. So to start it off, well, we just always assume we have some process running. I always like just saying it's process 100, and that is what we will assume that starts main. So up top here in the top right, typically I just write like the parent-child relationship. So we have process 100. It's just chilling by itself. It's not doing anything. So when we go through this, I mean, it's easier to do on this because I can move text. So process 100 will start executing. It will execute this line, which will create a variable called I and assign it equal to 4, right? So process 100 will have an I, and it will be equal to 4. So is I equal to 0? No, so it will process 100 will go into this loop and then fork, right? So we're going to fork. We're going to create another process. Likely, what is the number I'm going to get back? Let's just assume we create process 101. So process 101, I'll move it a bit here. Oops. So process 101 is a child of process 100, right? So for each process, what will fork return in process 100?
The PID of the child.
Yeah, the PID of the child, which is 101. So process 100 will return 101. Process 101 will return 0. And in process 101, if it's an exact clone of the parent, will it have a variable called I? Yes. What will be equal to? 4. So it will have an I equal to 4. And then the only difference is the return value of fork. Both of them will create a variable called PID and then assign whatever fork return to it. So in process 100 or 101, it will be 0. In process 100, we'll get PID equals to 101. So everyone okay so far? All right, do we know which one is going to execute next? No, right? So in this case, doesn't really matter what one we assume goes first. In order to not have to write as much, I'll just pick the one that I know will go into this else branch and exit, so I don't have to write it anymore. But there's no reason why it executes first other than it just helps me a little bit. So process 100 will, PID is not equal to 0, so it will go in this else branch, and then it will print off what's the current value of I? 4. So it should print off 4, not necessarily in any order. Not in order. So let's just assume that that executed. And now it would call exit. It's kablamo, it's done. It's not executing anymore, right? So process 100 is now dead. So we're all good there. It might have printed out 4. All right, so if process 101 executes, is PID equal to 0? Yep, so it will decrement its I, right? So I will decrease from 4 to 3. Then it will just follow the logic. It will skip over the else, come back up here. Does I equal 0? No, so it will go ahead and fork again. So process 101 will fork. That will create a new child process of it. So it will likely get, I don't know, process 102, creative names. I don't know, pinky color, sure. Process 102. So we have process 102 going. Will it have a variable called I? Yes, what will the value of I be? 3, right? Same as the parent whenever it called fork. So it's going to be an exact clone. Process 101 is the thing that called fork. Well, then the current value of I is 3, so it will also have an I of 3. So it would have lost that PID variable whenever it escaped the scope of the loop 2. So now we have these two processes. So in process 101, what will fork return? Yeah, 102, right? It created process 102. So process 101 would create a variable again called PID. It would be equal to 102. And in process 102, PID would be equal to just 0. All right, so both of them would want, we don't know what's going to execute next. It might be process 101. So if 101 executes, well, PID is not equal to 0. It would go in the else branch. It would go ahead and print off, in this case, 3. Again, not in order. So is there any reason why I couldn't see 3 before 4? No, right? I could have just not executed process 100, and it could just sit around waiting to execute. I didn't necessarily have to execute it, so I could see 3 instead of 4, or 4 before 3. There's no set order here. So I would print that off. Should I continue with this, or does it look pretty much the same thing? Like it's just going to go through again. This would eventually, yeah, can I fast forward a little bit? All right, so eventually process 102 is going to print out 2, not necessarily in that order. It's going to go again, come up, do another fork. It's going to fork, create another process, let's reuse colors, whatever, create another process called 103. It will have a copy of I. I will likely be equal to 2, to 2 that time. It will go through and, decrement, blah, 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 and I'll just see from that process eventually printing out 1. So I'm going to see 4, 3, 2, 1, not necessarily in that order. Whenever the process that decrements I to 0 goes, that process would just go up, check the while again. When I is equal to 0, it will break out of the while loop, just return 0, it won't print anything, process will be dead. So I'll see 4, 3, 2, 1 printed, not necessarily in that order, any order is possible. Any questions about that? Everyone good with that? Okay, what else do you want me to do? Yeah?
So 353 midterm that you wrote.
Yep.
Question number 18.
Of last year?
Yeah, 2023.
Or 2023?
2023 ECE344.
Okay, so I only have 2024 handy. What do you know what that question is? All right, first off, yeah, for studying stuff, go to my website. If you want to see all of the past exams, courses, archive. So 353, exact same course as this course. Also CS111 at UCLA, exact same course as this one. These 2 exams are a bit weird because they're the COVID ones, but this one's also relevant. Don't worry, UCLA people are not smarter than you. That is not a first-year course. Anything that starts with 3 digits there is a 3rd or 4th year course, so it's a 3rd-year course. They just name things silly. But you wanted specifically this exam, midterm, what question?
18.
18.
It's like 18 and 21 and 22.
21 and 22. So this is an odd system with page tables. All right, so odd system, page size of 256. So I will just write it on this that you can't see. So 256, that's 2 to the 8 byte page size. And then it says 16-bit virtual addresses. And our PTE size is 16 byte. 16 byte, which is 2 to the 4 PTE size. Okay, so, and then 32-bit physical address. 32-bit. So, first one you're okay with. How many PTEs can you fit on a single page? Again, that's just page size divided by PTE size, so should give you 16. And then the next one says, if we use multi-level page tables, how many levels of page tables would we need? Show your work. So for this, go here. Oh, hey camera. All right, so for this, if we have a 16-bit virtual address, we have that page size. So the page size should immediately tell you how many bits you need for an offset. So how many bits do I need for an offset in this scenario? 8 bits, right? It's just log 2 of page size. So this means 8-bit offset. So if I have an 8-bit offset, I know if my virtual address size is 16 bits, so my virtual address which is 16 bits, it's always in 2 parts. There's the offset, and then there is the VPN. So if my offset is 8 bits, My virtual address is 16 bits, and how many bits do I have for VPN? 8, right? 16 minus 8. So if I have multiple levels, right? My scheme always for multiple levels of page tables is I want to fit all one level on exactly on a page. So the question before, that number of PTEs per page. So from the question before, that was 2 to the 4, which means, well, that's how many I can fit on each individual level. So in order to pick which one, I basically use log 2 that to get the number of index bits I need, right? So in this scenario, if I use multiple levels of page tables, I need what? 4 bits for an index, right? And then you can either do it visually or try and remember the equation. The number of levels I need of page tables is equal to ceiling. Always have to round up because I'm using pages. I can't use half a page. I'm just dealing with pages. Is the number of virtual bits minus offset divided by index bits. Or if you want to do it visually, like this whole thing is just the number of VPN bits. And basically, how many levels do I need to cover all of this? So in this case, it would be ceiling of whatever, 8 divided by 4, which is 2, right? So I need 2 levels of page. All right, so that was 18, right? So what's the other one? 21 and 22. So 21 was, for this system, could you use a smaller PTE size? If so, what is the smallest power of 2 that would be appropriate? So remember, very important, PTE, what are 2 pieces of information that is in a PTE that you should know off the top of your head? Yeah. Yeah, it will store at least, always, 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 it will store the PPN and then a valid bit. Might be other permission bits that you could argue, but at minimum it needs a valid bit. So if the page table entry size is 16 bytes, how many bits is that? I guess it's too early to multiply by 8, but that's 128 bits, right? That's a whole hell of a lot of bits. So if we have a 32-bit physical address, right? So here is our 32-bit physical address. We know we use 8 bits for the offset. So how many bits would we need for the PPN? 24, right? So the minimum size of my PTE would be those 24 bits for the PPN plus a valid bit. So it needs to be anything greater than or equal to, was it 25 bits? So we could make it a hell of a lot smaller, right? So if I wanted to, 32 bits might be appropriate to store all that information. It would give us 8 bits for permission, other permissions if we wanted to. You could also argue if we need at least 10 bits for permission, then, well, the next power of 2 is 64 bits. So we could make it smaller, right? There's no reason, since the PPN is so small, no reason we couldn't make the page table entry size, you could argue 4 bytes or 8 bytes. Either one would be fine, but 16 seems a bit overkill. It's way too many bits here. So for that, I would say, well, you could argue that it does not need to be 16 bytes. It could be, you could argue 4 or 8, doesn't matter. So either is fine as long as you say it needs at least, the main thing here was just figuring out the PPN needs 24 bits, at least a permission bit, and then you could assume other permission bits if you want, but it needs at least a valid bit. So it could be smaller. And then question 22 just says, for the PTE size above, would the system see any benefits in terms of access time? So in terms of access time, our access time for virtual memory is just pretty much dominated by how many levels of page tables we have, right? So in this scenario, if I make my page table entry smaller, well, that means I can fit more page table entries on a single page, right? So if I reduce it to, I don't know, 8 bytes, that means I can fit 2 to the 5 on a single page now, right? Which would mean I'd need 5 bits for an index. Or if I argued that I should only use 4 bytes for my page table entry size, that means that I could fit 2 to the 6 on a single page, which means I'd have 6 bits for the index. But either one we do doesn't matter. So if we change this denominator here in the number of levels to 5 or 6, I mean, most impactful would be if we changed it to 6. So 8 divide 6 is like, what, 1.3 or whatever? I don't know, it's too early for math. Whatever that number is, or 1.25, whatever, it doesn't matter because we have to round up. We might use only a quarter, I guess, of the page table, but it doesn't give us any levels. We still have 2 levels, so it won't improve our access time. All right, anything else to go? Everyone loves virtual memory. So you want me to start going over this one? This one's probably most relevant to you. This is the one from last winter. So, or do you want me to just whirlwind through all the old slides or point out stuff? Yeah, this one. All right. Want me to just start the virtual memory question since we're on that? Sure, I saw some. So this will be like yours, right? You'll have this page of functions just in case so you don't have to remember them. Fork, exec LP, dup2, wait PID, pipe, exit, write read, pthread create, exit, pthread join, pthread detach. So you will be given that so you don't have to write a cheat sheet. So let's go here, virtual memory. All right, this says we created a experimental machine, which is a bit silly, with a 16-bit virtual address, 8-bit physical address, page size of 16 bytes. So again, whenever I see a page size, I can't help it. I have to write it in powers of 2. So this is 2 to the 4. And since that is the page size, that directly log 2 of that is the number of bits I need for my offset. So I could also write here for offset bits. And then page table entry size of 1 byte. Here, you know, it's a bit silly, but I'll write that in powers of 2 too. That's 2 to the 0. And then it says our page table entry has the following layout where the physical page number is the most significant 4 bits, and the permissions are the least significant 4 bits. So this is how it is read to you. You'll see that this is slightly convenient because, well, 4 bits is exactly 1 hex digit. So this is 1 hex, this is another hex. So a byte is just 2 hex characters, and you can figure out which one is which without having to write it in binary. So here is a dump of physical memory. So the rows and the columns, if you add them together, that tells you what the byte is at that address. So each of these, they're 2 hex digits, so they are a byte. And it says to read it, for example, which has a typo. So this should be FF. So it says, for example, the byte at address 24, which would mean if you want to find out what the byte is at that address, it would be this row and this column. So it would give you this byte right here, FF, that is the value at that address. So, first one, it says how many bytes would we need to store a single level page table if we used it? So, single level means we're not bothering to fit a page table on a page. It will be as big as it needs to be. So how would I go about figuring out how big this damn big page table needs to be? Ruh-roh. Yeah. Yeah, so page size, 16 bytes, so we have the offset bits there. Where do I go from there?
You find the PPN.
The PPN? Yeah, how many bits I need for the VPN, right? Because each virtual page needs a page table entry for it.
You need 4 bits for the VPN.
Yeah. Or 4 bits for the VPN. Do I?
Wait. Oh, no, 12.
Yeah, 12. So first off, I need to figure out how many virtual pages I have in this system. So your virtual address, question says that it is 16 bits. And it's always, always, always the offset and the VPN. And for multi-level page table, we break that VPN into multiple levels because we want each smaller page table to fit on a page, but still, we're just translating a VPN to a physical page number through the page table entry. So our offset here is 4 bits, which means our VPN has 12 bits, right? Everyone agree with that? So how big our page table needs to be if we just have one big one? Well, how many page table entries do we need? Uh-oh.
Wait, how many page table entries for what?
How many page table entries do we need for this system to translate every single VPN? 2 to the 12, right?
500.
Yeah, I can just leave in powers of 2. So for a big, just one big page table, I need a page table entry for every single VPN. So the number of VPNs I have is just, well, if I have 12 bits, it's just 2 to the 12, right? So I have 2 to the 12, and then each of those needs an entry. So under this system, I mean, it's a bit silly because each page table entry is a single byte, but I'll just write this in case, you want it. So it's however many entries I need times the size of an entry. Basically, it's just one big array. So in this scenario, that's just 2 to the 12 times 1 byte, which means it's 2 to the 12 bytes, or 4,096. I don't care. You can bring a non-programmable calculator to the exam. Likely it's just going to slow you down. Just leave in powers of 2. I don't care. It gets the point across. All right, so okay with that?
Just one question.
Yep.
How do we know if we have to use the VPN to find it?
How do you know if you need to use the VPN to find it?
How is it done? Like, not in the calculation, just like the initial question.
So it's always the point, if we use a single level page table, we need an entry for each VPN, right? We need to translate it, always the case.
And how do we know if we want to
So it's the same for the multi-level one. We need an entry for each individual one, but with the multi-level page tables, right, we're wasting a bit more space because we're fitting each smaller page table on a page, but it needs to be able to have an entry for each individual one, right? So like with the multi-level page table, even for our normal system, right, we have an L2 that can point up to like 512 things, have an each L1 can point to 512 things, and then each L0 can point to 512 different things. Well, if you look at that, that means across all the L0s, right, I could have 512 L1s, and then each of the L1s can point to 512 L0s, and each of the L0s, that's where the direct translation is. So that can be, that's basically 2 to the 9 to the power of 3, right? How many entries are across all my L2s, which is 2 to the 27, which for our normal system, right, which has 27 bits for the VPN, same thing, right? And remember we argued that, hey, if we had one big, large page table for this system, that would take a gigabyte because, well, we'd have 2 to the 7 VPNs and our page table entry size is 8 bytes. Yeah, so exact same thing here, just the numbers are different. And multi-level page tables, all we do is break off that VPN to multiple levels. But we always need a page table, at least one page table entry for each, well, not at least. We need exactly one page table entry per VPN.
Thank you.
Yeah. Okay, so next question. What is the minimum number level of page tables we need in our system? Oh, God damn, everyone. Gee, this multi-level page tables, we hate it. What's the one rule for multi-level page tables, though? Uh-oh. The one rule.
Like it has to obey like the press
No, yeah. Need an L2.
Like you need a P0.
You need a P0.
You need something to translate to the entries. Like you need a root page table.
I do need a root page table, but what's like the main idea behind multi-level page tables? Why am I breaking it up? Save more memory. Yeah.
Accesses, I guess. No, you make more access.
Yeah, well, also to make allocation easier, right? The main idea behind multi-level page tables is I have each of my smaller page tables fit exactly on a page. It's always what you want because the operating system's just going to deal with pages. I'll use some pages for data, some pages for page tables. So in that case, whenever it asks multi-level page tables, you should immediately figure out how many entries should fit on a page, right? And it's basically always the equation is, well, if we have our page size, we have to figure out how many page table entries can we stick on a page. So it would just be the number of PTEs I can fit per page is equal to per page is equal to the page size divided by the PTE size, right? It's basically just an array. And typically, you'll have 2 of these and you'll have to figure out 1. So in this case, let's see if we can see it. Do I know the number of page table entries per page? No. Do I know the page size? Yes. Do I know the PTE size? Yes, so I could figure it out. So in this case, my page size is 2 to the 4. My PTE size is 2 to the 0, which means it's just 2 to the 4, right? That is the number of page table entries I can fit on a single page, which that always tells us the number of bits we need for an index, right? If we need to figure out what entry on this page we want to access. So here we would need 4 index bits. right? And then let's just use the easier equation. So the number of levels we need is ceiling VPN bits divided by index bits. How many VPN bits do we got? Yeah, 12. And we just figured out we had 4 index bits. So what's 12 divided by 4? 3. You'll have a calculator too, just in case. So 3 levels. Everyone okay with 3 levels? All right, next one says we're going to, the fun part. So first off, if we have 3 levels, that should make sense that, well, our VPN is 12 bits. We have 4 bits for index, so we need 3 of them to cover all of those 12 bits. So on this, I can write out here my virtual address, again, which is 16 bits. I can write it out several different ways. One is the offset is 4 bits, and then the whole VPN here is 12 bits. But for the multi-level page table, right, I'm breaking that up into 3 levels. So in this case, I would have an L0 index, an L1 index, and an L2 index. If I only had 2 levels, I would only have an L0 and an L1. L1 would be my root, it's the highest level. If I had 4 levels, I'd have an L3. So you have to be careful. It's not always just L2 is the highest. Depends how many levels you have. So each of these is 4 bits. You can sanity check yourself, add up everything at the bottom. 4 plus 4 plus 4 plus 4 is 16, so that's all good. So now it says we have a virtual address of 39C. So 39C, the first 3 questions ask us what's the page offset, what's the index of the highest, what's the index of the lowest. So if I just took this virtual address 34C in hex and broke it up into all those parts, what goes where? So it should be the case that is for my offset. C, right? I should just write it out. C3, I'm dyslexic, 3C43, and of course there would be a leading 0, right? So this would be just 0. So for this virtual address, it nicely lines up with all the hex digits. So my L2 index would be 0, L1 would be 3, L0 would be 4, and my offset is just C, aka, what's that, 12, right? So first question says, what is the value of the page offset in this virtual address? C, right? C or 12, whatever, I wasn't picky. What is the index in decimal of the highest level page table? So what is the highest level here? L2. What's the index for this virtual address? 0. What's the index of the lowest level for this virtual address? 4. So the lowest level is the L0 index, which is 4.
Isn't it representing the value?
Representing the value?
Yeah, I don't understand.
It's just what's the index of the lowest. So if we take this virtual address 34C in hex, and we divide it up into, which bits make up the L1 index, what bit makes up the L2, what makes up the L0 and what makes off the offset. Turns out, well, each are 4 bits, so each hex digit represents a different thing, right? So C, that represents our offset. And then this, the next least significant bits, that's our L0 index, right? And then 3 would be our L1 index.
And then 0 would be the L2 index.
Yeah, and then there's a leading 0, and then 0 would be the L2 index, which is up here too. So whenever it says highest level page table, that's the highest level, so the biggest number of L, so in this case it's L2. So that's why our index is 0 for this virtual address. The index of the lowest level page table will always be L0. So we want the L0 index for this virtual address, which is just simply 4.
Okay, and then like, what is the value of the page offset? So that would just be 0xc, but if they were saying like, what is the index of the page offset, what would that be?
So there is no index of the page offset. So there's just the bits that make up the offset. So the value of the offset in this case is just the lower 4 bits, which is just C.
Because I was getting confused because I was thinking that like the value represents the index and the index represents the value.
No, just the index is just the value of the index. So it's just take the number there.
The value at the index.
Yeah, so you take that virtual address, you break it up, what parts represent the index, like which index, what represents the offset, and just tell me the value of it.
At that index, at the highest or lowest index.
Yeah, so highest level in this case is L2, lowest is L0.
And the value is like 0 and 4 respectively.
Yeah.
All right. Thank you.
Yeah, and then it says, for this virtual address, 34C, detail every step of the address translation, including the specific level of the page table and the page table entries accessed at each step. If a page fault occurs, identify the PT responsible for the fault. So this says that our highest level page table is at ppn 0. So if we have our physical address, right? That's good English by my part. It said we had 8-bit physical addresses. So our ppn would be 4 bits, and then the offset would be 4 bits. So ppn 0 represents all of the memory from 0, 0, so the least significant bit being all zeros, all the way to all ones, which should be those range of addresses, which should make sense because we said there are 16 page table entries per page. Each of our pages are 16 bytes, and each of them is 1 byte. So if we look at this, it should make sense that these 16 bytes, those are all page table entries, right? So if our root page table is at address physical page number 0, that means the first 16 bytes are our L. In this case, this is our L2 page table, right? So if we're translating this address, so this address is 034C. Well, to translate it, we start at the L2 page table, right? We start at the L2 page table. We look at the page table index at index 0. So index 0 would mean this entry, right? So this entry, if we access this entry and we look at what the page table entry layout is, if it's F, it's all ones, which means this is a valid entry, and it means the physical page number is 1, right? So if the physical page number is 1, that means that's the physical page number of the L1 page table, right? Which means the L1 page table starts here. So this is now being used for this translation as my L1 page table. So it says detail every step, every specific level, and the page table entries accessed each step. So you would say L2 page table, PTE is, which is valid, right? So now in the L1 page table I'm going to use, I look up index 3. So this is index 0, 1, 2, 3. So this is my entry I'm using in L1. That is also valid, right? So this means F there, I'll just erase a little bit. F there means it's valid, and it would use physical page 2 for my L0 page table, right? So over here, I would write L1 page table, PTE is 2F, which is valid, which means I use 2 here as my physical page number, which means this is my L0 page table. And I'm shortcutting, so I'm supposed to use index 4 here. So that means 0, 1, 2, 3, 4. So I'm using FF. So that means there the PPN is equal to F, and it is valid, right? So this is my entry in my L0 page table, so that tells me what the final mapping of this VPN to PPN actually is. So that means L1 page table, PTE is FF, which means that my final resulting address is just going to be, I'm just going to replace the whole VPN, which was 034, just with the PPN I got from that entry. So it would be just F, and then the offset is changed. So that would be my final address. Good? Yeah?
Just a question, do you have solutions for all the midterms on your website?
Yep, there's solutions for everything, and you can ask me, and yeah, let me know. Yeah, there's solutions to everything on my website. And yeah, only 2 minutes, I guess I can't do anything else. But also, the other class, I did different questions. If you want to look at that recording too, I did this midterm, I did I did the threads question here and the process question. Yeah.
How did you decide where like the L2 page table just chose like the first one?
So how did I decide where the L2 page table is? I was told from here. Yeah, because you need to be told that, right? Otherwise, you have no idea where to start. So yeah, I'll be around to answer questions too. I think that's it. Also, another thing you should be thinking of, since I just wrote the midterm, should I say this? Whatever. I could throw in like creating P threads with forking and make it even more fun. So remember the rule, if you have P threads, you have multiple threads and you fork, the new process gets created with just a copy of that thread. So even if you have, not like you'd have 8 or anything on the midterm, I'm not that mean. But if you had a couple, the new process only has a clone of whatever was created. Yay. Yeah, I'll leave it at that vague thing. Yikes. All right, well, good luck. And just remember, pulling for you. We're on.